Recording. Perfect. Again, hello everyone to who is joining us live and who is watching this video after recording. My name is Balnor Mindigalieva, and I'm a PhD student in petroleum engineering at Colorado School of Mines. I would like to introduce Aleta Finnila, our speaker for today's bootcamp number 5. But prior to that, I would like to remind everyone to stay mute, and if you have any questions, feel free to put them in the chat or wait until the end of the presentation to unmute yourself to ask the questions. So now I would like to invite Dr. Aleta Finnila to the floor to tell us a little bit about herself and to introduce us to the microseismic interpretation of UW data.
Great. Thank you so much, Balnor, and welcome everyone. As Balnor said, my name is Aleta Finnila, and I work with WSP USA, and I've been involved with the Forge project for probably the past 5 or 6 years in charge of their fracture model for the geothermal reservoir. My background is in geology. I got a PhD in geology from Brown University in igneous petrology, actually studying early history of the moon. And then went to work as an IT consultant and a programmer for about 6 years. And I've been with, I joined Golder Associates, which is a geologic consulting company, about 9 years ago. And then we were acquired by WSP, more of a engineering consulting firm, about 2 years ago. So we're now known as WSP USA. And I'm going to be talking about the fracture model we developed for the Forge project. And I presented this work at the Stanford Geothermal Workshop in February. So there is a paper that describes what I'll be talking about. And I also presented it at the Forge Modeling and Simulation Forum in October, which was recorded as well. So that would be available on the Forge website if you needed some more information about that. I'm going to start off talking just a little brief introduction to what the fracture model is that I'll be discussing. There's a class of models called discrete fracture network models. You'll hear them as DFN models. And this is where we're sort of explicitly modeling the void space in the rock. So what you see in the pictures here, you see these sort of hexagonal features. Those are representing just circular fractures in the rock. The software that I use is the FracMan software that was developed within Golder Associates over the last 30 years. And for simplicity, sometimes we represent sort of a circular fracture as a hexagon. So don't be confused why you see all these hexagons in here. And that being said, we don't actually believe that fractures are perfectly circular either. These are approximations. And one thing I would encourage you is when you're thinking about developing your fracture models, you can be restricted to fitting planar features to the microseismic data, or you can come up with more complex shapes too. You don't have to be restricted to planes, but that certainly is simpler, and that is traditionally what is done in a discrete fracture network model, where we have collections of fractures in the rock. And it's those connections between the individual planar features that is creating flow paths within the rock that we want to exploit to extract the heat and pull that for the geothermal system. So at Forge, we have this fracture model, and we use it for a variety of purposes. We would like to be able to predict sort of initial pressure responses to pumping in the wells. We would like to predict, say, the long-term pressure and temperature response when we're actually producing between a set of 2 wells, an injection well and a production well. There's a variety of responses that we can model with these models. And what we're trying to do with this project and the Datathon here is to come up with some other interpretations of the recently gathered microseismic data that we have. I think you had in some previous introductions to the Forge project. You know, there's this injection well 16A that was drilled and then subsequently stimulated hydraulic fracturing. So adding water at pressure, enough pressure to break some of the pre-existing natural fractures, break them open a little bit to allow for more permeability, or to create even new fracture pathways based on the high pressure water being injected. And these are just some more pictures of fracture models. So this was an early model of the site where one of the early wells, a vertical well 5832, is shown here. And what you're seeing here is where the subsurface granite, the top of the granitic bedrock, is shown sort of at the top here. So there's alluvium above it that you're not seeing. But then once you get into the bedrock, you're seeing sort of this fractured granitic rock down below. And again, we're sort of showing these planar features as fractures in that rock. And another sort of close-up view just along, say, a vertical well borehole here. This is just cutting a cylindrical slice out of that rock and showing again fractures in that rock. So these planars cutting through here would be fractures intersecting that. Just to give you an idea of what some views of a DFN model might look like. So the early models, we did have a lot of data to build those early fracture models. We had a geologic model. We knew of some existing faults nearby, not actually cutting through the forage reservoir site, but in nearby areas. We had well temperature logs. We had image logs, including electrical resistivity of the of wells that actually penetrated through that geothermal reservoir. So we actually did have some information about fracture orientations, where they intersected those well boreholes. We had outcrop trace maps from the nearby mountains where we saw fracture orientations where they were seen at the surface. We have core testing data, hydraulic well tests, et cetera. So a lot of data goes into these initial models. So we have sort of our DFN fracture model, and that's what we'll be talking about today. But those models feed into, you can use them to develop continuum models of the site. You can use them for other kinds of discrete models, such as finite element models and discrete element models. And we had teams of people working on those models as well, where normally we would start with the fracture model, create this DFN model, and that would sort of be the starting geometry used by these other modelers. And then these are just some of the things we can then simulate during hydraulic stimulation. We can examine what we might want for a stage spacing, what to expect for different well separations, injection pressures, and also do some prediction for long-term production. So these are useful models. I think the uptake is coming up with a fracture model can be a very useful exercise. So I encourage you to pursue that. Now we do have the micro earthquake catalogs available from that 16A stimulation. They're available on the GDR, and I believe you've had a presentation on the GDR previously. So the work that I'm showing here used the first edition of those catalogs, which was available in April of 2022. I think there's a second edition now on the GDR available that has a few more data points. So I would assume that's the one you're using for this project, but I'm not positive. So this is just the data looks very similar between those two versions. So what you're getting in those catalogs is you're getting events, microseismic events that have been captured during the stimulation of 16A. So as they're setting up, there were 3 stages that were stimulated. There was the open hole at the very toe of that deep 16A well. And then there were 2 stages in the cased section of the well above that that were perforated and then stimulated with the high pressure water. So what they do when they do these stimulations is, in this case, they did sort of a explosion at the source, at the injection point, which creates a little micro earthquake that they can record on the monitors. So you'll see under location, you'll see there's some events that the first one is called the check, the L2 check. And that is the event. So that should be occurring right on the borehole. So we know that location. Then the other points in the catalog that we're getting are fitted, sort of triangulated points, fitted points for their location, where we're given X, Y, and depth coordinates in a local coordinate frame that's explained in the input files there. We're also getting the moment magnitude of those events, so how strong a signal they are. We're getting a quality term and an error term. So the quality they explain in the files. So the quality is dimensionless measure where higher values are indicating a more reliable event location. So that can be a useful feature of this data set. And they're also giving an error estimate where the error is sort of an estimate of the maximum error in the event location. And that's given in units of feet. So you can sort of get an idea of what the potential error in those locations are. Okay, just a little bit more about the error. So this is showing a sort of side view of the well 16A. So it starts vertical, goes down into the granitic bedrock, and then gets deviated from vertical about 65 degrees for this lateral here. The open hole section is right here at the toe. And then the other two stimulation zones were stage 2 here, stage 3 here. You'll see those. And there were some estimates based on where the recording instruments were placed. So there were geophones placed in some of the vertical wells surrounding this well. And those geophones were recording the seismic events. So by sort of combining all the data coming in from the geophones, those are these sort of points shown here on these vertical wells. And they also collected data at the surface. So they had things collecting there. But there was a paper produced before the stimulation estimating the amount of error expected given the locations of the geophones. Now, during the actual stimulation event, some of the geophones were not working. So some of the errors were larger than predicted, but that's listed in the input files for this the earthquake catalogs. So just as when I was first looking at this data, I just wanted to plot the locations of the check shots. So those were ones where we knew the locations. Those should be in the stimulation events in relation to the actual well trajectory. So this is sort of a top-down view of that 16A lateral, where the thickened sections are showing the stimulation zone. So that's the large 200-foot open hole section at the end of the well. And then you have stage 2 here in a perforated section and stage 3 here in a perforated section. And this was just showing to give me an idea about how much error we were seeing in those locations. So loading this earthquake data into some sort of visualization software is going to be critical to the success of this project. Because it's really important to get some understanding. You're trying to create, say, fracture planes fitted through this data. So the idea is those microseismic events should be giving you some information about what the fracture geometry is of those fractures that are actually opening and responding to that stimulation event. And presumably, those same fractures would be the ones providing the flow pathways, which are going to be so important to understanding how this geothermal system sort of evolves and works. So what you're seeing here at the bottom in blue, this bottom blue trajectory is the existing well 16A with the stimulation zones shown in white. About 100 meters above that is a projected sort of a suggested production well. So that would be 16B. It's not drilled yet. So that's sort of a potential future well location site. But then all the points here are showing you the microseismic events in the catalogs. There's one for each stage. So there's 3 catalogs, one for stage 1, one for stage 2, one for stage 3. And the color coding here is giving you some indication of the timing of the events. And also the size is showing you the moment magnitude of those events. So being able to visualize that data, I think, is going to be extremely important. Then the next series of slides I'm going to show you is the workflow that I went through to come up with a DFN model based on that microseismic data. So this is the same exercise that you're going to do, but hopefully you're going to come up with different workflows to come up with different fracture models at the end. And as I'll explain, I can justify the workflow that I came up with, but there was a lot of artistic license. There were a lot of choices that I made that you might make different choices on. So keep that in mind when I'm showing you sort of an example of how I approach the problem. And you might share some of this workflow, or you might do something completely different. And that would be great. We're trying to see some different approaches to how to incorporate the microseismic data into developing a fracture, sort of a revised fracture model for this site. So what I did is in my software, and as I said, I was using the Fracman software, but other software is available for visualizing point data sources. So I visualized the point data for each stage, showing the time evolution, and then I rotated it in 3D, sort of without a perspective on, because I was trying to see planar features. So if I rotate that point cloud in space, if there's a planar feature where a bunch of the microseismic data might line up on a single plane, if you rotate that sideways, that might show up as a dark line if you're looking sort of at that projected in 2D. So just trying to identify where there might be planar features, I was doing it very manually, just sort of visual inspection. Once I visually identified a set of points that I thought might represent a plane, I created a plane in my software to be sort of an estimate, a rough estimate of what that fracture feature might be. And then I collected all the data points within a certain distance of that plane. And so that then gave me a subset of microseismic data that was presumably representing a planar feature. And then given the error, it doesn't all line up exactly. That's why I said, oh, give me all the points within, say, 10 meters or 20 meters of this planar feature that I'm visually seeing. Grab all that subset of points. Then I can just do, then I can actually fit a plane to that set of points. So I was using a PCA algorithm just to fit a plane to that points, gave me a center of the plane. I could fit a radius to it, and gave me the orientation. So then having that information, I went back and created that particular fracture in my model. So knowing a center location and an orientation and a size for it. So that's how I went through and I manually fit 4 planes for stage 1. I fit 5 planes for stage 2, 2 planes for stage 3. Again, there's no set number of the appropriate number for what I was doing at the time. Having fewer features was nice because of if we're going to use these models for numerical modeling, sometimes having a simpler model is more efficient. We can handle that a little easier, but we don't want to make it so simple that we're losing some important complexity. So how many features are fit per stage? That's an open question. What would be appropriate? Then it was obvious that those planar features that I fit did not all intersect. They did not create a single flow path. And we certainly know that the flow paths that we're interested would be connected. There's also plenty of literature that shows there could be existing flow paths that do not give off a would not respond to stimulation such that we would see a signal. So there could be features, there could be fractures in our model that are connecting these features that we don't see a signal for. So I added a few extra fractures to connect my model together. So we would have flow paths that would be connecting one fracture to another. And again, that was very much artistic license, but we do have information about expected orientations of fractures in this model from the previous work we've done. So from the image logs of wells passing through this, this reservoir, we do know a lot of information about what the expected orientations are. So I added some connecting fractures based on that prior knowledge. And then it's important once you've created your DFN, you've created these fracture planes to visualize it and just to visualize that with respect to the original microseismic data. And I was checking to see that my planes were at least incorporating the most significant events, so the largest in moment magnitude. And I wanted to make sure that my DFN was reaching sort of the extents of the stimulated zone to capture that. So it's important to, once you fit your planes, to go back and look at it along with the original data. So my task, I looked at the data given in the GDR, and I wanted to clean up the data a little bit for my use. So the kinds of things that I did with those original files, I was removing white space from those Excel spreadsheets. I was calculating an elapsed time in seconds for easier visualization, because they were giving sort of times in dates and times. So I calculated an elapsed time in seconds. For fitting the fracture planes, I was removing the check shots. You don't need to do that. In fact, maybe you'd want to keep that. So so that was sort of step one, cleaning up the data to put it in a format that works for whatever simulation software you're using. And then what I'm showing here is sort of, as I was saying, we had some prior knowledge of the fracture orientations that might be expected. This was coming mostly from the resistivity logs from the wells. And we had information from drilling 16A. So we knew information from 16A itself. We also had information from some of the vertical wells in the system. But there were thousands of fractures that were identified that way. And their orientations are shown in what's called a stereo net here. And I don't know if all of you are familiar with that, but it's showing, in this case, the normal poles to fracture planes in sort of a polar coordinate frame. And it's important to know when you're looking at a stereo net to know if it's an upper hemisphere projection or a lower hemisphere projection. This one's an upper hemisphere one. But from this, we can read orientations of planes. And what we found was 4 distinct sets of fracture families where we sort of show a mean pole, so a mean orientation for them. But you can see from color, there's some spread on the orientations we actually find. So these contour plots are showing sort of the intensity of like how many planes we would expect to see in particular orientations. So the hotter colors are showing sort of a concentration of orientations, where the cold blue is we weren't seeing so many orientations plotting on the stereo net in those. So we did have some idea of some orientations that might be more likely than others. And I include this slide here just because if we're talking about finding planar features in this data set, those were going to be represented we talk about their orientations in 2 ways. So oftentimes we talk about the fracture poles. And so that's just the vector normal to that plane. And we also sometimes talk about the fracture dip vector. And the dip vector lies within the plane and shows the the direction of the steepest incline on that plane. So we talk about there's two sort of equivalent ways of defining your orientation. You can talk about the pole. So we describe that with a trend and plunge, or we could talk about the dip vector, and that would be sort of a dip direction and a dip angle. So you might see those two terms. So you might have to look up, if you're not familiar with how to describe these things that geologists often do, you might need to look up these terms. All right, so getting to the data, this is showing the microseismic points for stage one. Stage one, remember, is this open hole section, the 200-foot length at the end of the well. And it's color-coded with time. So the blue colors are the earliest responses, whereas when you get to green, yellow, and here's a red one, it's very small. Those are the later time events for that stage. And just as I said, I would rotate these points in 3D and go through my workflow, and I came up with these sort of 4 planar features to that data. And you see I'm not capturing everything. So it was just a choice on my part as to what to consider a plane or not. And this is where I would love to see some other choices made here. Let's see. I am showing the sizes scaling by the moment magnitude as well. So the larger events are shown as larger sort of spheres there. Stage 2 is shown here, and there were 5 fracture planes that I fit to that data there. So you're seeing sort of a side view of the well. And here was the stage 2 injection point. And my results for stage 3 injection point here, I fit 2 planes, one large there and one smaller one there to the north. And then these are the 4 connecting fractures that I just added. So these were just added based on my need to connect those fit fractures. I needed to connect them so I could have flow pathways and to reach, say, some, make sure that I was extending the model to what seemed to be the full stimulation extent. So I added a few. So my model had only 15 fractures in it. And this is the picture that you've probably seen for this fracture model. Just the color coding here on the fractures is the stage. So the stage 1 fractures are in purple, stage 2 is in blue, stage 3 is in gray, and then the connecting fractures are in orange. There. So an interesting thing to do once I had my model, and I would encourage you to do something similar if possible when you come up with your models, is to show your features with respect to what we're expecting from image log data. So again, I'm showing, based on all the orientation information we were predicting for the Forge model, and we have known some orientations of fractures that match this distribution. What I'm showing here is I'm plotting the features that I fit and showing how most of them cluster, certainly for stages 1 and 2, we're clustering around the same orientation as this south striking, moderately dipping west set. So that's where I was fitting most of my features. Stage 3, I was getting one feature that lined up very well with what you'd expect from a simple hydraulic fracture, sort of creating a new feature in this model, sort of near this south-southwest striking vertical set, and also another vertical one that didn't really line up too well with either of these 2 sets. But stage 3 is in purple here, so those were vertical fractures oriented here. And then my connecting fractures are shown in red, where I was sort of adding in features where I thought were likely, given what we knew, either knew about the existing fracture orientations or just I needed to in order to connect the fractures. This one was just seemed to line up well with some of a few microseismic data points, not enough to say fit a plane for, but there was some justification for adding this feature there. So it's nice to show just how your predicted fracture model, is it consistent with what we've seen before? And it does not need to be consistent. It's just an interesting comparison to make. And what I show here too is based on the stress conditions of the site, what orientations might be expected to slip or open during stimulation. And so that's sort of another analysis that you could do if you want to incorporate the local stress conditions. And what I was showing is here it seemed like a lot of my features might be the ones likely to fail in a shear slip mechanism. Whereas certainly for stage 3, right along the edge here, those are features that I would expect to be just opening, just dilating, and not necessarily slipping, just expanding and taking pressure. So another way to sort of just present your results that would be interesting. So in the GDR, the work that I did is available because we were using those models for other stimulation work and we wanted to make them available for the community. So what you've seen here is available on the GDR in this download. And what I included was the DFN, the 15 fracture DFN, plus the well trajectory of 16A in those same coordinates. And I think I include a PDF of a presentation that has some similar slides to what you're seeing here. I present my fractures. What I'm providing is a fracture XYZ coordinate, which is my global coordinate frame. So that's different from the coordinates, the local coordinate frame that was provided in the micro earthquake catalogs. So you have to decide on what coordinate frame you'll be using for your work. And I'm providing a fracture radius, so a size estimate, and then an orientation. I'm providing that in both ways. So I'm providing both the fracture pole vector as a trend and plunge and the fracture strike and dip as well. So two equivalent ways of showing the orientation of those planes. And then I had sort of starting guesses for what the fracture aperture might be, what that permeability would be, and a fracture compressibility. Those values would need to be estimated with other ways. So that's not part of your project. Your project is to come up with a geometry and not necessarily the fracture properties such as aperture and these things. So I think the workflow that I'm showing, some of the advantages of it is it's pretty simple, right? It can be performed before we did not have any focal source mechanisms available or cluster analysis available on that microseismic data. If you do have this information, that might be another very useful way to subdivide the microseismic data ahead of time, showing that there might be subsets of points that might be coming from a single plane. You could discriminate that way, but we didn't have that. So this kind of analysis can be done without knowing that, just based on the locations of those planes. And we certainly did utilize prior knowledge of the fracture system. So when I was looking for fracture planes, I had sort of some samples up there of orientations that might be expected, and that helped my eye perhaps identify those, perhaps induced some bias though. So maybe we don't want to sort of include that prior knowledge. It's a choice. And this method, you can customize how many features you want to fit and what size you want to fit those planes to based on what your ultimate use of your fracture model is for. So you can choose that. But why kind of I think this is exciting to have all you attack this problem is, this was a very manual process. sort of relying on that individual interpretation. It's not very scalable. It just takes too much time to look for those things. And it's a little unconstrained as far as adding those connecting features, what I'm saying, probably aseismic features that I'm saying are there. We don't know exactly where they are, but they're probably there connecting these features. It'd be awesome if we had some way of justifying the location of those features. And I did not utilize that knowledge. We were given some information about the location error, the quality of the data. I looked at the timing and that was helpful, but I did not utilize all the information available in those micro earthquake catalogs. So that might be helpful. I just wanted to say this work was funded by the U.S. Department of Energy. So we've been working on this project for a number of years, and I want to thank you for your attention. And I'm going to stop with the, I think I can take some questions now. If desired, I could also go through, I could show you the points in the Frachman model, and I could show you some examples there, but I think I'd first rather take questions.
So if anyone has questions, please feel free to put them either in the chat or unmute yourself.
Yeah, hello, this is Samuel.
Hi.
I have a quick question. So when connecting your points, I was wondering, why didn't you start from the injection point? Why didn't you connect from the injection point? Since we definitely know that fluids will come from that point, right?
Yeah.
And so the fractures will propagate from that point to where your fractures are.
I think that's a great question. I think probably if I'd thought about it, I probably would have done so. So the interesting thing is, so stage 1 was 200 feet long. So it's not known when you have an open hole section of a well, there are a number of pre-existing fractures that are intersecting that. So the place where you're going to initiate is not really well known. So even with the check shot, so we had the check shot, the actual injection areas, there could be multiple fractures feeding it. So stage 1, we don't know. It was 200 feet long. We really couldn't fit a point. And that might have just, because I knew that, maybe I didn't try too hard with stage 2. Stage 2 ended up matching pretty closely. I did add this little hydraulic fracture to connect what I saw as this plane here. So I placed the hydraulic fracture right at the injection zone. So I wanted my connecting features. I did do that. And stage 3, actually the plane that I fit without including the injection point actually lined up with it very well. So I didn't need to do it there. So I guess I didn't feel the need to, or maybe I did, in the sense of I added this connecting fracture. Stage 1 was quite mysterious because there were not very many microseismic points near the injection, near the stimulation zone. One of the reasons for that, however, could be there was some prior stimulation that happened in stage 1. And once you stimulate the rock, say once you crack it open, if you re-stimulate it later on, you might not be getting a microseismic signal. It's already opened. So there was sort of there wasn't much information near the well borehole. That being said, they made an effort to really refine in the second version of the catalog, which is available now. They did make a big effort to look closer to the well bore in stage 1. So I think there's more information now about the near stage 1, which would be very useful to look at.
No,
that's a good question.
Okay. I have a second one. So this is a quick one. So what's the difference between the quality in the catalog? Can you go to the catalog?
Yeah. It's and I don't know that I'm gonna actually, the alls I know is what is what is said in the text. So I don't have any special information about what these things were. I wasn't involved in this, but I think there is more information available, hopefully, that explains this. But
yeah.
So they explain it here.
Quality, the difference between the quality and the error, right? So because I'm guessing, I mean, they are synonymous.
Well, so I'll read this here because it might be too small for everybody to see. So quality, what it says is a dimensionless measure of the event quality. It is the ratio of the bootstrap stack amplitude to the long-term stack amplitude, usually in the range 2 to 10, where higher values indicate a more reliable event location. So to me, it's sort of a function of the magnitude. It's a ratio. So it's looking at the actual, microseismic signal coming in. And I think the ability to extract that signal from noise. So if it's more consistent among all the, I'm not a seismologist, so I can't get into the details. But for me, the quality might be, when they're evaluating all those waveforms coming from all the different signals, how easy it is to pull out that signal from the noise. That's to me what it means. Whereas the location, that is, even if it's a really distinct signal from all the different locators, you would get, if you can't quite get them all to agree, if you can't really triangulate very successfully among all the different points, that's where you're sort of getting a distance measurement of error.
Okay.
Yeah. So they're kind of, I think they are different. Yeah.
Oh, okay. Yeah, makes sense. Okay. Thank you very much. Appreciate it.
So next we have Daisy Nin raising a question. So you can go ahead and ask your question. Afterwards, we will address the questions in the chat.
Okay, yeah. Thanks so much for the presentation. Really appreciate it. So I just have a question about the fracture orientation, because based on the it's like the rose map. So the strike and the deep angle for different fractures are very different. And also I noticed that there is very shallow deep angle selected. How is this possible? Because based on our experience, it seems like we would say that lots of hydraulic fractures created should be vertical or maybe near vertical. Why is the deeping angle so small?
Yes, so this is why a fracture model seems to be very significant for geothermal systems, certainly in bedrock, is because we're actually the vertical features. Let me go to so let's go. I'll talk about here. So if we're creating a new hydraulic fracture, we are, given the regional stresses, we are expecting a vertical feature. And that is what we're seeing in stage 3. Stage 3 was very different from stages 1 and 2 in that it was using a viscosified fluid. So it seems to have behaved very differently from the slick water treatments that were done in stages 1 and 2, where you're trying to reduce the viscosity of water in order to allow the fluid to penetrate more deeply. And so I think we're seeing 2 very different behaviors here. So I think what we're seeing in stages 1 and 2, you're not creating much in the way of new fractures. So the existing stress state is important, but it's not allowing you to create new vertical fractures. What it's doing is it's allowing you to pressurize existing fractures in the system, which are for the most part not vertical. They have orientations. When they were created a long time ago. They've been rotated. They're very complex. So what you're seeing, I believe, is you're seeing these existing natural fractures, which are not vertical, that are cracking open, they're slipping and producing these microseismic signals. And the fluid pathways would be expected to be more tortuous. We would expecting the fluid to be going through these inclined systems as opposed to a shortcut through one hydraulic feature, which is what we're seeing in stage 3. So the fact that we're not seeing vertical features in the microseismic signal in stages 1 and 2, to me suggests that we are utilizing the existing fracture network, natural fracture network. We're not necessarily creating much in the way of new vertical hydraulic fractures.
Okay, I see. So following up about this question, so meaning that for the DFM model that we picked, meaning that we are not only selecting the hydraulic fractures, but also the possible pre-existing fractures.
Correct.
That's why it's possible that those fractures, they are intersecting with each other. They
Yes.
are not parallel with each other.
Yes.
And okay, I see.
Yes, and that's good news for a geothermal system, in that if we're trying to maximize fracture area in order to extract the most heat possible, we would rather have a system like this, where the fluid has to travel through a complicated pathway and is exposed to more fracture area than a simple shortcut perhaps between two. So
yeah, but another question is okay, what's the connectivity among the different fractures? So that's that's a different question.
Yeah.
Okay, yeah, thanks. Yeah, really interesting. Thank you.
Okay, so next question we have in the chat. Apologies if I mispronounce the names. The question is asked by Israel Momo. May I know how you fitted the plane?
Yes. In fact, this is a well, so I used so eventually the algorithm I used a PCA analysis in a subset of points that I looked at. So, for instance, I don't know if you can see this. So what I'm showing here are the stage 3 microseismic points here. And so sort of my workflow was to sort of rotate these around in space and look for linear patterns. So if I go sort of vertical, it's kind of a vertical view, all of a sudden I'm seeing 2 lines here. I'm seeing a line sort of this way, and I'm seeing a line up there. So, if I just looked at it here, I don't see much, so this is where I'm rotating it. I'm looking for linear features. So this is what I would do. I would just manually manipulate this point cloud in various ways. And depending on how you do it, you might see different things, right? But when I said, okay, I see what I think is going to be a linear feature, I went ahead and created a little fracture plane just in my software here and said, okay, subset all the points within, I think 20 meters of this one. So let's see, I connected my subset. Let's see, stage 3, filter 1. Okay. So for this big feature on stage 3, I grabbed all these pink points. I said, okay, I'm going to say those belong to one big fracture. I exported those, and then I wrote a little Python script just to fit, to fit a plane in 3 dimensions to that. So I used a PCA where I chose where you're just looking at the smallest eigenvalue, the vector associated with the smallest eigenvalue to get the normal to that fracture plane. There's other ways to do it. I mean, basically just fitting a plane to a 3D set. Yeah.
Dr. Finnila, I think you were not actually showing the screen that you were describing.
Oh my goodness. So you're not seeing.
Yeah.
Are you not seeing?
Yeah, we're still seeing.
Oh,
the
you're still
screen
seeing
with-
you're still seeing the PowerPoint. Okay,
Yes.
I'm sorry. Thank you. Thank you for stopping me. I was really excited by what I was showing you there. Let's see. Let's do.
And we were trying to interpret what exactly.
Let's see. I'm going to stop that share and I'll share a different thing here. Let's share screen. Here we go. Share. Are you seeing something different now?
Yes.
Okay. Sorry. Let me go back to you. So what I'm showing here is this is all the microseismic data for stage 3. And you can look at it with different views. You know, you look at it this way, I'm like, well, I'm not sure I see any planes there. If I look sort of vertically on this one, all of a sudden my eye is picking up 2 linear features. Sort of, I could say I could fit a big plane to this feature here. Are you seeing my mouse?
Yeah.
Yep.
Okay. And I can fit a smaller vertical feature up to the north side here. So I could see, my eye sees 2 lines that sort of simply capture most of the microseismic data. So then I said, okay, well, I'm looking at this, the big one first. Let me just visually, I'll stick a plane in there, and I created a little plane. So I think, yeah. So this is a plane that I just manually eyeballed. And then I said, okay, get me all the microseismic points within 20 meters of that plane. So I got that subset. 3 there. So if we just sort of toggle, you can see I'm getting rid of points that I think don't belong to it. Which is interesting now that I look at it, like, why is this big one like not associated with it? A little troubling, but it lines up nicely. Anyhow, and then I exported those points. I said, okay, that's my subset. These points represent a planar feature, actually. Even, and I'm saying they don't all fall on that line because there's some error in the location. I'm just saying. Or realistically, it could be some smaller fractures that just sort of are being connected mostly by a hydraulic fracture. And so there's some variation in there, but I'm going to represent it as a single planar feature. So I exported that. And then, as I said, then I used my Python script to just fit a plane to it that gave me a center, a vector, normal to that plane. And I fed that back into my software to actually show the fit one. So connect those on 3. What is this? So page 3. A little hard to see. Not that one. Oh, I see. Yeah. So here in the darker green, that was the plane I just eyeballed. And then exported those points. And then the plane in gray, you can see it's very similar, but it's a little different. That's the one I actually fit using the principal component analysis. And so that's once I did my PCA, I got a radius and a center and an orientation. And then I created this feature. So those are the steps that I went through. And then I exported my DFN, exporting sort of as you showed. So the centers and just exporting the information about each fracture. Did that answer your question?
So Israel Mama, if you need follow-up, yes, he says thank you. Next question we have from Sushma Ban. The question is the reliability of data fed into model checked for quality, aka accuracy, or it's not important?
Well, I guess as far as I know, I didn't develop a measure of quality. I'd be interested to, we don't know. I don't know what criteria you would use, but I'm open to suggestions. So, because we don't know the truth, right? We don't. So it's hard to know. You can come up with measures like how many, of your DFN, what's the max, you could come up with the distance to any particular feature. You could come up with some quality estimates, but I'm not sure there's a meaningful one, I guess. So interesting question. And if you could come up with some measures of quality, I think those could be debated. I certainly don't think there's any, I certainly haven't come across anyone saying there is a known way to evaluate the quality of the results here.
Thank you. Next question is from Bilal Aslam. The question is, did you perform any calibration to the MEQ fitted DFN model to the bottom hole pressure / pumping data to reduce the uncertainty?
I guess the answer would be no, but I'm not sure exactly what we would be calibrating here. Could the person maybe explain a little bit more?
Bilal, feel free to put more in the chat.
Okay, hello. Thank you for the opportunity. I mean, did you use this DFN model for dynamic simulation later and compare?
Oh yeah. So yes, this has been used now for dynamic simulation. And there was a Stanford Geothermal Workshop paper in February that talk about the results. And in fact, I think you were given that maybe in your problem statement. I think you were given a reference to the paper from the Stanford Workshop that used this model as basically the DFN model. And then they were doing, as you say, they were doing well, okay, I guess they were using it for modeling the future. So as far as the calibration, we did do the work to calibrate it against the pressures as well, but that might not have been, that's a different, I don't think we published that. Yeah, oh no, we did. So actually, that work was published in the last conference, the Geothermal Rising 2022. There's a paper by Pengju Xing, last name Xing, where that's exact. So he was using this DFN to do the calibration and the pressure modeling. And what he found in his work was they had to add a few extra stochastic features in to get the pressure. Like just using these 15 fractures wasn't enough. They needed to add in a few more fractures, which makes sense. I mean, that's not surprising. But I think the takeaway for me from their work in that paper was that it was support that stages 1 and 2, the pressure support was most consistent with flow paths utilizing natural fractures. And stage 3, the pressure response was fine using just like a simple hydraulic fracture. Like you could match it pretty well with that. Whereas stages 1 and 2, which we're getting the sort of more complex, a complex microseismic response, that pressure support was indicative that the natural fracture, the complex natural fracture system supported that better. So.
Okay, thank you. I will check on that paper for the details.
Okay, so next, I would like to, so we have actually a comment from Sushma Band regarding the question on reliability accuracy. I would like just to read that. The comment is, I would assume, excuse me, the experts should specify criteria for what's quality data or not. Otherwise, feeding any inaccurate data would impact the outcomes. So Sushma agrees that some preliminary work needs to be done to define quality metrics. And we have last, if you would like to comment.
Oh, I just wanted to comment there that, yeah, I mean, that might be something that the committee running the program would come up with.
And we have the final question. We will take 2 more questions. So we have another question from Daisy Nin. The question is the selected fracture plane orientation consistent with local stress?
So there were several fracture planes, right? There's several fracture orientations that in our DFN, and the largest fracture, in stage 3, that one is consistent with what you would expect from the stress regime for a new hydraulic fracture forming. A subset, a majority of the features that we fit from the microseismic data were those dipping to the west, sort of moderately dipping to the west. Those were very consistent with the natural fracture set that we see from FMI, and that natural fracture set is consistent, that is expected to fail in shear more readily than many other orientations. So I'd say the DFN, the 15 fractures DFN set that I came up with is consistent, but there's other features that are a little maybe more surprising. So yes and no, that is something you can compare to and say, would you expect these orientations or not? Yeah.
Thank you. The last question is coming from Jeff Boudier. The question is, I see that Fragment is a proprietary software. For this Datathon, we can only use open source frameworks. Are we on our own as far as finding open source DFN modeling software? So I can answer this question. I mean, what I can say is that we're going to have an kickoff meeting on April 3rd, where we will have a speaker defining the challenges more in depth and also guiding you to which open source softwares you can access to fulfill the task of this Datathon. Okay, so there is one more question. Jeff Bailey is asking, where's the analysis of the image log located on GDR?
Yeah, so I think you would have to look up, it's, you could look up, I think it's like 16A log data. It's in there. So I don't know what the link is offhand. But you can track it down from the Forge website and also from the GDR.
Perfect. We have Andy Adams sharing the link to the requested data. Okay, so lastly, I would like to thank you, Dr. Finnila, for taking the time and introducing us to this wonderful interpretation you've done. We're very appreciative and thankful. And before we wrap up this meeting, I would like to just make some reminders. I'm trying to send everyone the text. Okay, so I've shared the text with all of you in the chat, which is basically a reminder that there's an upcoming kickoff meeting happening on April 3rd at noon Central Time. And the Zoom link was shared on Slack. And if you haven't joined it yet, which I encourage you all to do, it's in the chat. And please remember to form the teams by April 10th and update Ben Cassidy on Slack with your team information. And you're also welcome to partake this challenge solo if you wish so.
All right, thanks everyone. Bye.
Thank you. Thank you, everyone.
Thank you.
Thank you.
Thank you.